Tomorrow, a rock from another star system grazes Jupiter's gravitational boundary with precision that a Harvard astrophysicist calls a 1 in 20,000 coincidence. That alone should stop you cold. But the James Webb Space Telescope just found something inside it that stopped the entire scientific community cold instead. Deuterium. The exact isotope humanity is spending hundreds of billions of dollars trying to harness for nuclear fusion. At concentrations 10 times higher than any comet ever measured in our solar system, this thing is saturated with the fuel of the future, and nobody can explain why. 22 anomalies, 0 answers. The flyby is tomorrow. Stay with me, because by the end of this video, you are going to understand exactly why scientists are not sleeping tonight. Subscribe and follow along, because this story does not end when 3I Atlas crosses Jupiter tomorrow. The universe has been throwing objects at our solar system since before the Earth existed, and we are only now building instruments sensitive enough to catch them. The anomalies will keep coming, and when the next one arrives, this channel is where you hear it clearly, without the hype and without the hand-waving. You are going to want to be here for that. Now let's get into it. Tomorrow, something threads a needle in space that has no business being threaded. An object from another star system, something that formed around a different sun, in a different corner of the galaxy, possibly billions of years before our solar system even existed, will reach its closest approach to Jupiter. And when I say closest, I mean closest in a way that should make the hair on the back of your neck stand up. The distance at closest approach is approximately 53.6 million kilometers. Jupiter's Hill sphere, the gravitational boundary where Jupiter's pull dominates over the Sun's, sits at approximately 53.5 million kilometers. That is not a coincidence that happens by accident. That is a razor's edge. That is threading a needle from another star system. The Hill sphere, in case that term is new to you, is essentially the bubble of gravitational influence around a planet. Inside that bubble, the planet is the boss. Outside it, the sun takes over. Think of it like the edge of a country's territorial waters. Cross that line and different rules apply. This object is skimming that boundary so precisely that Harvard astrophysicist Avi Loeb has publicly described the alignment as a 1 in 20,000 coincidence. 1 in 20,000. You have better odds of being struck by lightning twice. But here's where the story stops being about orbital mechanics and starts being about something stranger. While astronomers were tracking the flyby, 2 brand new research papers came in from the James Webb Space Telescope. And what those papers found inside the vapor cloud surrounding this object has upended the scientific conversation entirely. James Webb detected water vapor outgassing from the comet. Standard enough, but when scientists measured the chemical fingerprint of that vapor, they found deuterium concentrations nearly 10 times higher than the most extreme comet ever measured in our solar system. 10 times, not 10% more, 10 times more. Deuterium, if you are not familiar, is a hydrogen isotope. It has 1 proton and 1 neutron in its nucleus instead of just 1 proton, like normal hydrogen. It sounds like a minor chemical detail. It is not. Deuterium is the exact fuel that humanity is racing to develop for nuclear fusion power, the same isotope being pursued at ITER, the world's largest experimental fusion reactor currently under construction in southern France. We are spending hundreds of billions of dollars trying to collect and concentrate deuterium on Earth. This object is apparently saturated with it, and it just grazed Jupiter's gravitational boundary with precision that a 1 in 20,000 probability can barely explain. Now, before anyone gets carried away, and I know some of you already are, scientists are not saying this object contains a fusion reactor. They are saying the isotope ratio tells us something about where and when this thing formed, and that something does not fit our existing models particularly well. Avi Loeb has now cataloged 22 separate anomalies associated with this object. 22 observations that do not behave the way we expect comets to behave. Any single one of them might be explainable. All 22 appearing in the same object is a different kind of problem. Before we get to those anomalies, though, we need to go back to the beginning, because the discovery of this object was already bizarre before any of this happened. In July of 2025, a telescope network in Hawaii called ATLAS caught something moving across the sky in a way that did not quite fit. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. It was built to scan for near-Earth objects, asteroids, comets, things that might one day inconvenience our planet in a very permanent way. On a routine survey night, the system flagged a faint, fast-moving point of light drifting against the background stars. Initial classification was unremarkable. Astronomers assumed they were looking at another inbound comet, one of the thousands that swing through the inner solar system and eventually curve back out again. Standard procedure: run the orbital calculations, refine the trajectory, add it to the catalog. The orbital calculations came back wrong. Or rather, they came back with an answer nobody wanted to see. The object was not on a bound orbit. It was not swinging around the sun and heading back out the way it came. It was moving too fast, approximately 60 kilometers per second, on what is called a hyperbolic trajectory. A hyperbolic trajectory, in plain language, means the object is moving faster than the sun's escape velocity. It is not going to stay. It was never going to stay. It came from somewhere else. It is passing through, and it is leaving. 60 kilometers per second, to put that in context, is fast enough that even our most capable spacecraft, probes like Parker Solar Probe, which only reaches similar speeds during its closest passes to the sun, barely rival it under optimal conditions. This object is doing that constantly, in open space, on its way out. Hyperbolic trajectories are the fingerprint of interstellar origin. An object born in our solar system will always be gravitationally tethered to the sun. In some way, even on the most extreme elliptical orbits, it eventually comes back. Something arriving from interstellar space carries the velocity of its home system, its journey across the void, and the gravitational interactions along the way. It does not belong here. It is passing through the way a bullet passes through a room. This was only the third time in recorded history we had confirmed an interstellar intruder. The first was Oumuamua, discovered in 2017, an object that generated more scientific controversy per kilogram of mass than almost anything ever detected. The second was Borisov, discovered in 2019, more comet-like, less controversial, but still extraordinary. And now this one, designated 3I Atlas, where the I stands for interstellar and the 3 means we are getting surprisingly good at finding these things. The naming convention is almost understated for what these objects represent. Direct physical samples of material from other star systems, arriving on our doorstep without an invitation. Within weeks of discovery, the observations were already getting uncomfortable. Because when astronomers turned Hubble toward it, the size estimate came back in a way that quietly broke several assumptions at once. The Hubble Space Telescope measured the nucleus of 3I Atlas at approximately 2.6 kilometers in diameter. That sounds almost modest until you compare it. Oumuamua, the first confirmed interstellar visitor, was estimated between 100 and 400 meters, cigar-shaped, small, easy to miss. Borisov, the second visitor, clocked in at roughly half a kilometer to 1 kilometer. 3I Atlas is several times larger than either of them. It is not dramatically bigger in absolute terms. We are still talking about a few kilometers of rock and ice, not a planet. But in the logic of interstellar detection, size matters enormously. Here is why. Detecting an interstellar object passing through our solar system is extraordinarily difficult. The window where something is close enough to detect but not yet past us is narrow. The probability of catching any given object depends on how many of them exist, how fast they move, and how big they are. When scientists run the numbers backward, starting from detection frequency and working outward to estimate the population, the results for objects the size of 3I Atlas become uncomfortable. If objects this large are passing through our solar system frequently enough that we can catch 3 of them within a decade, the galaxy must contain them in truly staggering numbers. We are talking about trillions upon trillions of objects, drifting between star systems in the darkness between galaxies. The conventional explanation for where these objects come from involves planetary formation. When solar systems form, the process is messy. Planets accrete from a disk of gas and dust, and the gravitational chaos of early planetary development flings enormous numbers of smaller bodies outward. Comets, planetesimals, chunks of ice and rock that get ejected before they ever settle into a stable orbit. Our own solar system almost certainly fired off billions of such objects into interstellar space. Other star systems presumably did the same. Over billions of years, the galaxy would accumulate a kind of interstellar debris field, the combined exiles of 10 billion star systems. But Avi Loeb has pointed out a mass budget problem with this explanation. Take the estimated number density of interstellar objects implied by our detection rate, multiply by the typical mass of an object the size of 3I Atlas. The math produces a total implied mass that, when distributed back across individual star systems, requires each low metallicity star system to have ejected approximately 1,000 Earth masses of cometary material. 1,000 Earth masses. The entire rocky mass of a planetary disk is unlikely to reach that figure. The raw material may simply not be there in the quantities required to explain what we are seeing. Scientists are actively debating this. The models may need to change, or the explanation may need to change entirely. And then, someone turned a telescope toward the tail, and the model started looking even shakier. Comet tails are one of the most reliable features in astronomy, reliable enough that astronomers have been studying them for centuries, and the basic physics has been settled for decades. A comet approaching the sun develops 2 main tails. The dust tail forms when sunlight physically pushes fine particles off the comet's surface. This tail curves slightly and glows in reflected light. The ion tail forms when solar wind strips charged particles from the comet's coma and blasts them outward at high velocity. This tail is straighter and points almost directly away from the sun. Both tails point away from the sun. That is the rule. That is always the rule. Regardless of which direction the comet is traveling, the tails point away from the sun. It is one of those astronomical laws that gets taught in introductory courses because it has no known exceptions that are physical rather than apparent. 3I Atlas had a feature pointing toward the sun. The structure was narrow. It was collimated, meaning focused, like a beam rather than a diffuse smear. It extended hundreds of thousands of kilometers in the sunward direction, and it persisted for months. Astronomers call this kind of feature an anti-tail, and they do sometimes occur in comets, but almost always as an optical illusion. When Earth passes through the plane of a comet's orbit, the geometry can make it appear as though dust behind the comet is pointing forward. It is a perspective trick, not a physical structure. Scientists know how to recognize this and account for it. This was not that. The anti-tail of 3I Atlas appeared physically real, a genuine structure extending in the wrong direction, maintaining its collimation and brightness through conditions where a perspective effect would have faded or shifted. Solar radiation pressure should have dispersed it. The solar wind should have swept it away. It stayed. It was visible month after month in multiple telescope systems. And then, after the comet passed perihelion, its closest point to the sun, the anti-tail changed orientation, yet still pointed sunward. That last detail is particularly strange. A perspective artifact would simply vanish or rotate predictably. A genuine dust structure with no driving force would diffuse and fade. Something about this tail was being actively maintained, or was being produced by an ongoing mechanism, not a passive geometric accident. Some researchers began describing the behavior as consistent with an active jet system, rather than passive outgassing, meaning something inside the comet was firing material in the sunward direction deliberately enough to overcome the constant pressure, pushing it back. The word deliberately is doing uncomfortable work in that sentence, and nobody in the mainstream scientific literature is using it casually. But the structure was there, and the structure did not behave like anything seen before in a natural comet. That realization was only the beginning of the anomaly catalog. Because when the James Webb Space Telescope turned its infrared eye toward the vapor cloud, the results stopped the conversation entirely. Every element in the universe carries a fingerprint, and James Webb reads fingerprints better than any instrument humanity has ever built. Spectroscopy is the science of breaking light into its component wavelengths to identify what chemicals produced it. Every molecule absorbs and emits light at specific wavelengths, a kind of atomic barcode unique to each substance. When sunlight passes through the vapor cloud surrounding a comet, or when the comet itself glows in infrared, the resulting spectrum contains the signatures of every molecule present. James Webb was designed specifically to work in infrared wavelengths, which happen to be where water, organic molecules, and isotope variants leave their clearest signals. When it trained that capability on 3I Atlas, the data was unambiguous. Scientists measured the deuterium to hydrogen ratio in the water vapor streaming off the object. This ratio, abbreviated DH, is one of the most important diagnostic measurements in planetary science, because it acts like a timestamp and a birthplace indicator simultaneously. Water molecules form in environments where hydrogen and deuterium are present, and the ratio in which they incorporate those two isotopes depends heavily on the temperature and chemical conditions at the time of formation. Cold environments tend to produce higher deuterium enrichment. Very cold environments can produce dramatic enrichment. Scientists know what the ratio looks like across various solar system bodies. They have cataloged dozens of comets, asteroids, and icy moons. Earth's ocean water contains a deuterium to hydrogen ratio of approximately 0.015%. Typical solar system comets run between 0.03 and 0.05%, already enriched compared to Earth, which is itself one reason water delivery by comets is a slightly complicated topic. The most deuterium-rich comets in our solar system reach perhaps 0.1% under extreme conditions. 3I Atlas came in at approximately 0.9 to 1%. Nearly 1 in every 100 hydrogen atoms in its water vapor is deuterium. That is roughly 10 times higher than the most extreme solar system comet ever measured, and roughly 60 times higher than Earth's oceans. The papers also flagged anomalies in carbon and nitrogen isotope ratios, separate measurements that told the same uncomfortable story. This object did not form where our comets formed. It did not form when our comets formed. And it did not form under any conditions that our standard models of comet chemistry comfortably accommodate. The scientific community reacted the way it typically does when data breaks a model, with intense scrutiny, competing interpretations, and a quiet background hum of excitement that the publicly released papers do not quite capture. To understand why the deuterium number matters beyond the chemistry, though, you need to understand what deuterium actually is, and why humanity has been chasing it for the better part of a century. Deuterium is the second simplest atom in the universe, and it might be the most important fuel in human history, if we can ever figure out how to use it properly. Normal hydrogen has one proton in its nucleus. Deuterium has one proton and one neutron. That single additional neutron changes almost nothing about its chemistry. It still bonds to oxygen to make water. It still behaves like hydrogen in most reactions, but it changes everything about its nuclear behavior. Deuterium can participate in nuclear fusion reactions. When two deuterium nuclei are forced together under extreme temperature and pressure, they fuse into helium and release a neutron along with a significant burst of energy. When deuterium fuses with tritium, a related isotope, the energy release is even larger. These are the reactions that power hydrogen bombs. The challenge has been controlling them slowly enough to generate electricity rather than an explosion. The tokamak reactor design, laser fusion experiments, and the international ITER project in France all represent humanity's attempt to solve that control problem. ITER, which stands for International Thermonuclear Experimental Reactor, is being built to demonstrate that more energy can be extracted from a fusion reaction than is put into starting it. It requires deuterium fuel. That deuterium is extracted from seawater here on Earth, where it occurs at a concentration of approximately 1 deuterium atom for every 6,400 hydrogen atoms. We build industrial-scale separation plants to harvest it. The process works, but it is expensive, energy-intensive, and produces fuel at concentrations that are useful, but not abundant. 3I Atlas, by contrast, contains deuterium at concentrations roughly 100 times higher than Earth's seawater. If you could somehow process the water vapor streaming off this object, you would have extraordinary feedstock for fusion fuel. Now, I want to be precise here because precision matters. Scientists are not saying this object is carrying fusion fuel intentionally. They are not saying it was built around fusion. The isotope ratio is interpreted as a formation signature, a chemical record of where and when this object came together, not evidence of deliberate fuel storage. But I would be lying if I told you the coincidence has not generated significant discussion both inside and outside the scientific community. 1 in 100 hydrogen atoms, 10 times higher than anything in our solar system. The same isotope we are spending hundreds of billions of dollars to harness, arriving tomorrow at Jupiter's gravitational boundary. The mainstream scientific explanation for all of this is ancient comet chemistry, and that explanation has a serious problem. The leading scientific explanation for 3I Atlas is elegant, consistent, and almost certainly at least partially correct, which makes its mathematical difficulties all the more frustrating. The hypothesis goes like this. In the early universe, the first generation of stars formed from clouds of hydrogen and helium with very few heavier elements. Astronomers call this low metallicity, a confusing term that actually refers to the abundance of any element heavier than helium, not just metals in the everyday sense. As early stellar systems formed in these low metallicity environments, some of them would have contained planetary disks cold enough and chemically unusual enough to produce cometary bodies with dramatically elevated deuterium ratios. The temperatures in some of these early protostellar disks may have dropped below 30 Kelvin, 30 degrees above absolute zero, cold enough that deuterium enrichment in forming ice would reach levels far beyond anything in our own solar system. An object formed in such conditions, then ejected during the chaotic early dynamics of its home system, could theoretically drift through interstellar space for 10 to 12 billion years, older than our Sun, which formed 4.6 billion years ago. Interstellar space is cold and mostly empty. In the absence of nearby radiation sources, an object buried under thick layers of ice could theoretically preserve its original chemistry for timescales approaching the age of the universe itself. The deuterium ratio we observe today could be a direct window into conditions that existed before our solar system existed, before the Earth was a rock in a protoplanetary disk, when the universe was still figuring out what it wanted to be. This explanation is genuinely compelling. It draws on established physics. It does not require anything exotic. It fits the direction of the isotope data, if not its precise magnitude. Several serious astrophysicists have endorsed versions of it in peer-reviewed literature. But when Avi Loeb started running the population statistics implied by this model, asking not whether one such object could exist, but whether enough of them could exist to match our detection rate, the numbers stopped cooperating. And the problem is not subtle. It is order of magnitude uncomfortable. Statistics, unlike comets, cannot be outrun, and the statistics behind the ancient comet hypothesis have not been kind to it. To understand Loeb's mass budget argument, start with a simple question. If we have detected 3 interstellar objects in less than a decade of serious sky surveys, how many total interstellar objects must be passing through our solar system at any given moment? Astronomers estimate this using detection probability calculations, accounting for survey coverage, object brightness, relative velocities, and observing windows. The resulting number density of interstellar objects in the galaxy is large, but not inherently absurd. The universe is old, and star systems have been ejecting material for 10 billion years. The problem emerges when you multiply that number density by the mass of objects the size of 3I Atlas. Take the implied population. Assume they formed in low metallicity early star systems, as the hypothesis requires. Divide the total implied mass by the number of early star systems that could have produced them. The calculation, as Loeb has outlined it, produces a requirement of roughly 1,000 Earth masses of cometary ejecta per low metallicity star system. 1,000 Earth masses. The rocky and icy material available in a typical protoplanetary disk, the raw ingredient for all the planets, moons, asteroids, and comets in a solar system, is nowhere near that figure. Our entire solar system's worth of non-gaseous material does not approach that number. The proposed source population would need to eject more material than it plausibly ever contained. This is what scientists call the mass budget problem. It does not necessarily mean the ancient comet hypothesis is wrong. Models are refined and revised all the time, and there may be source populations or ejection mechanisms we have not fully accounted for. But it does mean the explanation, as currently stated, does not close. The numbers do not balance. You cannot produce the galaxy-wide population implied by our detection rate using the source material available in the star systems proposed as the origin point. Loeb's position is not that this proves anything exotic. He has been careful on this point in his public statements. His argument is that scientists should be honest about when the data exceeds the explanatory capacity of the current model. And with 3I Atlas, the current model is being asked to explain 22 anomalies, not just one. The chemical measurements were only the beginning. There is a specific kind of scientific discomfort that comes not from one thing being wrong, but from 22 things being strange at the same time. Avi Loeb has been one of the most publicly visible astrophysicists in the world since the Oumuamua controversy, and not always for comfortable reasons. His willingness to publicly entertain the possibility that some anomalous observations might have non-natural explanations has earned him both a significant public following and a complicated relationship with parts of the mainstream scientific community. With 3I Atlas, he has not claimed the object is artificial. What he has done is compile a list of 22 specific observational anomalies, measurements, and behaviors that do not fit standard comet models, and argue that the scientific community should confront them honestly, rather than explain them away piecemeal. The anomalies span multiple categories. Some are chemical, including the deuterium enrichment already discussed, along with unusual methanol production rates, anomalous carbon isotope ratios, and nitrogen signatures that do not match known comet populations. Some are structural, including the anti-tail behavior, the jet geometry, and the surface brightness distribution. Some are dynamical, including the non-gravitational acceleration and the trajectory geometry. And some are statistical, the coincidences involving timing, distance, and population numbers that seem to cluster around this object in ways that would be unremarkable in isolation, but become harder to dismiss collectively. Loeb has described an informal anomaly scale for interstellar objects. On that scale, 3I Atlas scores lower than Oumuamua, meaning it has more potential natural explanations for its individual behaviors, but still registers as significantly anomalous, given the sheer number of unusual features stacking up in one place. The critical point in his argument is not that any single anomaly is inexplicable. It is that independent anomalies occurring simultaneously in the same object suggests either an unusual natural origin that our models have not encountered before, or something more fundamental is being missed. Each individual puzzle piece might fit a natural explanation. The question is whether you can find one natural explanation that fits all 22 at once, and so far, nobody has published one. The most visually arresting of those anomalies is the jet structure, and when you see the images, you will understand why people have been arguing about it. Comet imaging is both an art and a science, and sometimes the most revealing images are the ones where you remove most of the information. A technique called Larsen-Cikanina filtering works by taking a raw telescope image of a comet and mathematically subtracting the symmetric brightness distribution, the smooth, radially symmetric glow of the central coma, to reveal asymmetric structures hidden beneath it. Think of it as removing a bright fog to see what is moving around inside. When astronomers applied this processing to Hubble Space Telescope images of 3I Atlas, the results produced one of the more unusual comet images in recent memory. Hidden beneath the coma glow, the filtering revealed 3 distinct mini-jets extending from the nucleus. 3 jets, separated from each other by approximately 120 degrees. 120 degrees. If you divide a full circle, 360 degrees, into 3 equal parts, each part is 120 degrees. The jets are, in other words, evenly spaced, symmetrically distributed around the nucleus with a regularity that natural random processes do not typically produce. A natural comet nucleus is an irregular, tumbling body covered in volatile pockets that can activate unpredictably as solar heating penetrates to different depths. 3 jets appearing at precisely equal angular separations is not the expected result of random volatile pockets on an irregular surface. The conservative scientific interpretation is that the nucleus has some unusual internal structure, perhaps 3 regions of high volatility arranged by some combination of formation geometry and rotation, and that this structure happens to produce symmetric jet outputs. Rotation of the nucleus could expose the active regions in sequence in a way that makes the symmetry appear more precise than it actually is in 3 dimensions. This is the mainstream working hypothesis, and it is defensible. But several researchers have noted, generally in informal contexts rather than published papers, that the geometry resembles the kind of thruster arrangement an engineer might design for a spacecraft needing to manage its orientation and direction. To be completely clear, that interpretation has no evidence behind it, no mechanism proposed for it, and no mainstream scientific support. It is the kind of observation that lives in the footnotes of serious discussions and the headlines of less serious ones. What is not in dispute is that the jets exist. Their geometry is unusual, and they have remained stable over extended observation periods. Natural jets on natural comets tend to evolve, shift, and sometimes extinguish as the nucleus rotates and volatile regions are depleted. These have persisted, and while the jets were commanding attention visually, a separate measurement was catching the attention of orbital dynamicists. Tracking the precise position of a comet over time is one of the most powerful tools in planetary science, because any deviation from the expected gravitational path tells you something is pushing it. Non-gravitational acceleration is a well-understood phenomenon in comet science. When a comet outgasses, when sunlight heats its surface and causes volatile materials to sublimate and stream off into space, those jets of escaping material act like tiny rocket engines. The reaction force pushes the nucleus in the opposite direction of the outgassing. For a typical comet heated primarily on its sunward face, the dominant outgassing is directed away from the sun. So the non-gravitational acceleration is directed inward, a slight push toward the sun, or in some orientations, a slight deceleration. This force is measurable and predictable enough that astronomers routinely include non-gravitational parameters when modeling comet trajectories. 3I Atlas shows non-gravitational acceleration with a significant component in the lateral direction, perpendicular to the Sun-comet line. Sideways thrust. This means the jets producing the acceleration are not simply pointing away from the Sun. They are firing at angles, producing forces that are pushing the nucleus sideways through its orbit. The possible natural explanations include a rotating nucleus where active jets spend time pointing in different directions, uneven sublimation patterns that happen to favor off-axis directions, or internal pressure pockets that redirect outgassing through the nucleus structure. These are all physically plausible mechanisms. None of them has been definitively confirmed as the explanation for this specific case, partly because measuring the internal structure of an object 2.6 kilometers across, moving at 60 kilometers per second, is not simple. What makes this particularly interesting is that lateral non-gravitational acceleration was one of the central anomalies of Oumuamua, the first interstellar visitor. Oumuamua accelerated away from the Sun in a way that could not be explained by gravity alone, and it showed this acceleration without any visible jets at all, which is why some researchers proposed the hydrogen iceberg hypothesis, and others proposed more exotic explanations. 3I Atlas has visible jets, which eliminates some of the mystery around the acceleration source, but the sideways component remains imperfectly explained. The fact that both confirmed interstellar visitors, numbers 1 and 3, show unusual non-gravitational dynamics is a data point that has not been lost on the people running the models. And then, there is the matter of the tail pointing in the wrong direction, which keeps coming up because it has still not been adequately resolved. The sunward anti-tail of 3I Atlas is, in the judgment of several researchers, the single most physically challenging feature of the entire object, not because it is impossible to explain, but because every explanation creates a new problem. To understand why, consider what it takes to push material toward the Sun from a comet in the inner solar system. Solar radiation pressure is constant and relentless. Photons, individual packets of light, carry momentum, and when they strike a dust grain, they transfer a tiny push. The sum of trillions of photon impacts every second adds up to a meaningful force on small particles. The larger the particle, the less effectively radiation pressure moves it, because force scales with surface area, while mass scales with volume. Large enough particles can partially resist radiation pressure for a while. This is why anti-tails sometimes exist as perspective effects. The large grains in a comet's orbital trail do not disperse as quickly as fine dust. But the anti-tail of 3I Atlas is not behaving like a collection of large grains being slowly dispersed. It is hundreds of thousands of kilometers long. It is collimated, focused like a beam, in a way that suggests a continuous source rather than a static cloud. It persisted for months without diffusing. And after perihelion, when the perspective geometry would have caused a true perspective anti-tail to vanish or reorient predictably, this one changed orientation, but continued pointing sunward. If the anti-tail consists of large particles, they need to be enormous, large enough to resist radiation pressure over months, and there needs to be a continuous supply of them streaming from the nucleus in the sunward direction. Calculating how much mass that requires produces numbers that strain the available budget for a 2.6 kilometer nucleus. If the anti-tail consists of smaller particles being actively accelerated sunward by some internal mechanism, a jet literally firing material toward the Sun, then you have a different problem. What physics drives a comet to actively eject material into a continuous stream against solar radiation pressure? Rotating jets could spend some time pointing sunward during each rotation, but maintaining a persistent, collimated stream over months would require remarkable stability in both the rotation and the active region. Some researchers have proposed magnetic field interactions between the comet and the solar wind as a possible deflection mechanism. Others have modeled unusual particle ejection geometries. The debate continues. What is agreed upon is that no single existing model explains all the observed properties of the anti-tail simultaneously. And just when you thought the physical behavior had exhausted the supply of surprises, the chemical analysis added another layer entirely. Chemistry does not lie, and the chemical profile of 3I Atlas has been sending mixed messages that depend entirely on which molecule you are looking at. Methanol is one of the simplest organic molecules. 1 carbon atom, 1 oxygen atom, 4 hydrogen atoms, combined in the most straightforward possible arrangement. It is commonly detected in comets and has been used for decades as a proxy for understanding outgassing rates and the volatile composition of cometary nuclei. Comets typically produce methanol at rates that scale predictably with their overall activity level, how much water they are producing, how close they are to the sun, how volatile their surface composition is. The relationship is not perfectly linear, but it is consistent enough that outliers stand out immediately. 3I Atlas is producing methanol at rates that are dramatically inconsistent with its water production. The ratio is off by a significant factor. If you calibrate your expectations based on the water vapor output, which is genuinely high and consistent with a large active cometary body, the methanol level should fall within a predictable range. It does not. The methanol is present in concentrations that suggest either a completely different interior composition than any known comet, or a separate source mechanism that is producing methanol independently of the standard volatile sublimation process. Methanol enrichment in comets is sometimes linked to radiation processing of organic ices over very long timescales, which would be consistent with the ancient comet hypothesis in a broad sense. But the magnitude here again exceeds the range that existing models can comfortably accommodate. What this tells us is that the chemical weirdness of 3I Atlas is not limited to deuterium. It extends across multiple molecules, multiple isotope systems, multiple chemical families. Each measurement from James Webb is adding a new line to the same story. This object did not form in the conditions that produced any comet in our catalog. Whether that reflects a truly ancient origin, a genuinely unusual stellar environment, or something else entirely remains unresolved. But the chemical fingerprints keep pointing away from anything familiar. There is a specific paradox embedded in the volatile chemistry of this object that has produced genuine disagreement among researchers, and it centers on a molecule even simpler than methanol. Methane is the most volatile common molecule in cometary chemistry. It sublimes at temperatures so low that it should evaporate rapidly as soon as a comet gets anywhere near the inner solar system. Comets that formed in the coldest regions of protoplanetary disks, beyond the methane ice line, can carry significant methane reservoirs. But those reservoirs are expected to deplete quickly under solar heating, and comets observed in the inner solar system typically show methane concentrations that reflect both their initial endowment and how much has already been lost on the inbound journey. The detection window for methane outgassing in an inbound comet is essentially a one-time measurement opportunity. Once it is gone, it is gone. James Webb detected methane outgassing from 3I Atlas at unexpected levels given its current position and thermal history. The complication arises from the timeline. If this object has been traveling through interstellar space for billions of years, exposed to cosmic radiation that slowly processes surface ices, the assumption would be that its most volatile components would either be gone or deeply buried. Yet methane is present, and its presence at the observed levels is difficult to reconcile simultaneously with the extreme deuterium enrichment, which implies ancient origin in an extremely cold environment, and with the anti-tail behavior and jet activity, which imply a highly active and thermally processed surface. You can explain the ancient cold origin, or you can explain the active volatile surface, but the same explanation does not easily accommodate both at the same time. This is the methane paradox. Not that methane exists, but that it exists alongside chemistry that should not coexist with it in the same object under the same formation history. Beyond the volatile gases, James Webb's infrared sensitivity opened a window into the organic molecule inventory of the object's coma, and what it found extended the chemical strangeness into territory that touches directly on questions about life in the universe. The coma of a comet, the extended cloud of gas and dust surrounding the nucleus, is a chemical reaction chamber. Ultraviolet radiation from the sun breaks molecules apart. Solar wind particles cause further reactions. The resulting mix of parent molecules, daughter products, and radiation-processed fragments creates a distinctive chemical signature that varies from comet to comet, but generally falls within recognizable ranges. 3I Atlas showed an unusual abundance of certain complex organic species, molecules containing multiple carbon atoms arranged in configurations associated with prebiotic chemistry. These are the kinds of molecules that astrobiologists get excited about because they represent chemical precursors to amino acids and other building blocks of life. In itself, organic molecules in comets are not new or surprising. Comets are widely believed to be important carriers of organic chemistry, and some models of life's origin on Earth involve the delivery of organic precursors by cometary impacts during the early solar system. But the specific profile of organics in 3I Atlas, combined with the unusual isotope ratios in its simpler molecules, suggests that its organic inventory may reflect formation chemistry that is genuinely unlike anything we have characterized before. If this object formed in the conditions implied by its isotope data, extremely old, extremely cold, in a chemically unusual stellar environment, then the organic molecules it carries are samples of prebiotic chemistry from a different epoch of galactic history entirely. That is a statement with implications that go well beyond comet science. And then there is the nickel. Nickel vapor in cometary comae was discovered in 2021, when a large survey of comet spectra revealed that nearly every comet observed by certain telescope programs showed nickel and iron emission lines in their inner comae. This was unexpected. Nickel has a very high sublimation temperature, meaning it requires significant heat to turn into vapor, and comets near but not extremely close to the sun should not be generating that heat at their surfaces. The leading explanation is photodissociation of iron and nickel-containing organic molecules, sunlight breaking apart complex organics and releasing metal atoms in the process. The discovery itself was a notable finding in comet science, resolving a decades-old mystery about metallic emission in cometary spectra. 3I Atlas shows nickel emission at levels that are elevated relative to the typical cometary population, particularly when normalized against its water production. The excess nickel is consistent with, but more pronounced than, what the photodissociation model would predict, based on its organic abundance. It could mean the object carries an unusually high inventory of nickel-bearing organic compounds. It could indicate a different photodissociation pathway. It could reflect a distinct surface composition that preferentially produces nickel-bearing species under solar irradiation. It is, on its own, perhaps the least alarming of the 22 anomalies, a quantitative excess rather than a qualitative departure from known behavior. But it adds another line to the ledger. Another measurement that points in the direction of unusual and away from familiar. And the chemistry, as remarkable as it has been, is only half of the story. The other half is about geometry, timing, and the mathematics of coincidence. Numbers are neutral. They carry no agenda, no ideology, no preference for one conclusion over another. But sometimes numbers arrange themselves in ways that make objectivity uncomfortable. The Hill sphere calculation is simple enough that you can verify it yourself. Jupiter's mass, Jupiter's distance from the sun, the sun's mass, these are well-established constants. Plug them into the standard formula for a planet's gravitational sphere of influence, and you get a Hill sphere radius of approximately 53.5 million kilometers. The closest approach distance of 3I Atlas to Jupiter during tomorrow's flyby is approximately 53.6 million kilometers. The difference is 100,000 kilometers. In solar system terms, that is essentially grazing contact with the boundary. It is the gravitational equivalent of walking along the edge of a cliff and stopping with the toes of your shoes over the drop. Loeb's 1 in 20,000 figure comes from statistical modeling of random interstellar trajectories passing through the outer solar system. If you take an isotopic distribution of possible approach vectors and flyby distances, the probability that a randomly incoming interstellar object would approach within this margin of Jupiter's Hill sphere boundary is approximately 1 in 20,000. This does not account for any selection effects, observational biases, or the possibility that Jupiter's gravity has influenced the trajectory. Indeed, an object approaching from the outer solar system would experience Jupiter's gravity over a long baseline and could, in theory, be drawn toward a closer approach. But even accounting for gravitational focusing, the precision of this alignment is difficult to explain away entirely. The more interesting question is what crossing or grazing the Hill sphere boundary actually means dynamically. An object passing exactly at the Hill sphere radius is in a gravitational balance point, momentarily in equilibrium between Jupiter's pull and the Sun's pull. For a natural object on a hyperbolic trajectory, this balance point has no practical consequence because the object is moving fast enough that it simply continues through and exits. But it is the kind of geometry that would be significant if one were interested in a gravitational interaction that was neither a collision nor a clean flyby, the maximum interaction zone that does not end in capture. Whether that observation carries any meaning beyond the interesting number is precisely the kind of question that serious scientists are reluctant to answer publicly. If you are familiar with the history of the search for extraterrestrial intelligence, there is a detail about the trajectory of 3I Atlas that has been circulating in online discussions for the past several months, and it is the kind of detail that is genuinely difficult to assess. In August of 1977, a radio telescope at Ohio State University, known as Big Ear, detected an anomalous radio signal that lasted for 72 seconds and matched several characteristics that SETI researchers had predicted would be associated with an artificial signal from space. The astronomer who reviewed the data, Jerry Amon, was so startled by what he saw that he wrote the word "wow" in the margin of the printout. The wow signal, as it became known, was never detected again, despite numerous attempts. Its origin remains officially unknown. The signal's intensity profile matched the telescope's expected response to a point source, suggesting it came from a specific direction in the sky rather than a diffuse source, and its frequency was close to the 21-centimeter hydrogen line, which some researchers had theorized would be a logical frequency for interstellar communication. The incoming trajectory of 3I Atlas, traced backward through space to its region of apparent origin, points toward the general region of the sky associated with the WOW signal's arrival direction. The alignment is not precise, the trajectory carries significant uncertainty, and the WOW signal's sky position has its own angular uncertainty. So this cannot be described as a confirmed directional correlation. But it is also not zero correlation. It is a coincidence that lives in the uncomfortable space between statistically meaningless and worth noting, which is the worst possible place for a coincidence to live if you are trying to maintain scientific equanimity. People who have looked at this carefully are divided between those who consider it a coincidence compounded by pattern recognition bias, and those who think it is worth including in the anomaly catalog without prejudging its significance. Neither group has the evidence to settle the argument. There is a specific kind of finality attached to this object that the terminology of science does not quite capture, and it is worth sitting with for a moment. 3I Atlas arrived in our solar system from somewhere we cannot precisely identify, traveling at a velocity that tells us it belongs to another star system we will never visit. carrying chemistry that reflects conditions we will never directly sample, on a trajectory that will carry it out of the solar system and back into the interstellar medium forever. There is no second chance. There is no follow-up visit. It has been here before, almost certainly, in the sense that it passed through this general region of the galaxy during its billions of years of travel, but it has never been close enough to the Sun to be observed. And once it passes Jupiter and continues outward, it will never be that close again. In perhaps 10,000 years, it will be as distant from us as the nearest star is today. In 100,000 years, it will be gone by any measure of the word. The data being collected right now, the JWST spectroscopy, the Hubble imaging, the ground-based photometry, the trajectory measurements being refined with each passing night, represents the entirety of direct scientific information humanity will ever have about this object. Every paper published, every model developed, every question answered or left open will be built on this narrow window of observation. And even within that window, our best instruments are operating at their limits. James Webb was not designed to track fast-moving solar system objects, and the scheduling gymnastics required to point it at 3I Atlas have consumed significant amounts of contested observing time. The Hubble measurements were made possible by a specific orbital geometry that will not recur. The situation is, in scientific terms, suboptimal. We are learning as much as we possibly can under difficult conditions about something that will never come back. That context makes the 22 anomalies feel different than they would if this were a recurring visitor. A short period comet that returns every decade eventually reveals its secrets, because astronomers can wait for better instruments and more favorable observing conditions. 3I Atlas carries its secrets with it. If the anti-tail is explained by a mechanism we do not yet understand, we will have to develop that understanding from the data already collected. If the deuterium ratio reflects formation conditions we cannot currently model, we will have to build the model from indirect inference. If there is something about this object that current science genuinely cannot explain, whether that resolves into new natural physics, a revised understanding of interstellar chemistry, or something else entirely, the resolution will require sustained scientific effort on data that is already in the archive. 3I Atlas is already changing how scientists think about interstellar visitors. It has complicated the population models. It has challenged the isotope chemistry databases. It has forced a genuine scientific debate about the limits of standard comet physics applied to extrasolar objects. It has produced 22 documented anomalies that will fuel research programs for years. Whatever the Flyby produces tomorrow, spectacular activity or complete quiescence, new surprises or confirmation of existing models, it will add one more data point to a case file that is already unlike anything we have accumulated for any other object. And when the object finally fades below the threshold of detection, smaller and colder and further each night, it will leave behind a scientific community that knows it has encountered something it does not fully understand. That might be the most important thing it could have told us. Not what it is, but that we do not know. Because science advances fastest, not when it confirms what we already believe, but when an object from another star threads a gravitational needle with 1 in 20,000 precision, saturated with the fuel of the future, pointing a tail in the wrong direction, and refuses to explain itself. We will be watching tomorrow, and the universe, as always, will decide what it wants to reveal.